In this part of the lecture, we'll discuss the topic of Lyapunov stability. But before we get into the depths of this, we'll try to understand why is this even important. And we'll do it through an example of a damped pendulum system. In the system, we see that we have the bob here, whose mass is m. The length of the string here is L, and theta is the angle that it has deviated from the horizontal, from the vertical line given here, and G is the gravity acting in this direction. With this, let us write the equations that govern the motion of this pendulum. Equations of motion. It's given by m L squared theta double dot plus m G L sine theta is equal to minus b theta dot. This is the equation of motion. The state space representation can be derived from the equations of motion. For the same, suppose we assume x1 is equal to theta and x2 equals theta dot. Then x1 dot is equal to theta dot, which is equal to x2. This is theta dot. And x2 dot is equal to 1 divided by ml squared minus mgl sine of theta, theta is x1, minus b theta dot again is x2. So in other words, we can rewrite this slightly as this, minus of 1 divided by ml squared. So m here gets cancelled. So what we have is 1 by L squared, and this again is one by ml squared. So this again is equal to x2 dot is minus g by L sine x1 minus b by ml squared x2. So this is a state space representation. So how do we calculate the equilibrium points of the system? The equilibrium points can be calculated by setting x1 dot equals x2 dot equals 0. These are the equilibrium points or the fixed points of the system. When we do this, what will we find? We will find that the equilibrium points, in our case, the pendulum oscillates in this manner only. It cannot cross over. So the equilibrium points pertains to theta lying on this line. Hence, let's have the state space representation. Hence, the equilibrium point is theta equals k pi for every integer k. However, what is valid in our case are only when k takes even integer values. Not only that, let's write it again. Additionally, we can tell very easily. So we have all studied it in the past and already have some basic idea of what exactly is going to happen. We know that as the pendulum starts oscillating, it will keep on moving in this manner, and the oscillations will gradually die out slowly, and the system will settle down here in this manner. Hence, theta equals 2k pi. Additionally, theta equals twice of k pi is not only a stable but also an asymptotically stable equilibrium point. What we'll just write is a stable equilibrium point. Remember that it is also asymptotically stable because it converges to theta equals 0. So how exactly? So can we now calculate? We have a set of equations here. Let us highlight the state space equations that we get. This is the first one, and the other equation is given by this. So these are the equations of x1 dot and x2 dot. Can we solve these equations and calculate what x of t is? The answer is that it is not very easy to do that. So how can we prove that the system will always come back to this point? We know that it is also an asymptotically stable equilibrium point. How do we say, since we cannot really solve it, we need to figure out some way in which we can show this. There is one other way, other than calculating all of the states. There's one more way in which we can say that. That is through the energy analysis. This forms the core of the Lyapunov theory, the Lyapunov tools that we will use. For the pendulum system given here, for our ease of reference, let us mention it here as well. This is our system. We know that the total energy of the system is the sum of its kinetic energy and the potential energy. So let's denote the total energy as E. The kinetic energy is simply given by half m L theta dot squared, and the potential energy is negative minus mg L cos of theta. So we can see that very clearly. The energy E is a function of both the states, theta and theta dot. So now we know that we can do this entire analysis in terms of the state space representation as well. This is x2, this is x1. This here is a function of x1 and x2. As the pendulum oscillates, what happens to the total energy of the damped system? Had it been an undamped system, the pendulum would have kept on oscillating continuously. However, since there is damping, we know that it will eventually settle down here. To see that, let us compute the time derivative of the energy. So this is the total energy, and now the time derivative of the energy, E, is given by dE by dt, and this is equal to so let's write it as this E dE by, okay, since we know that is a function of the states, so we'll write it as x1 times dx1 by dt plus do E by do x2 times dx2 by dt. If we solve it completely, we'll find that E dot or dE by dt is equal to minus of B times x1 squared. So this is a very important expression. Why? It tells us exactly how the energy changes with time. Let's look at the term on the RHS here. We know that this term is always, this entire term, including the negative sign, is always less than or equal to 0, meaning dE by dt is either decreasing or remaining constant. It does not increase over time. Two things can be shown for this system now. The first is, we know that the energy is strictly decreasing whenever this is not x1, this should be x2. This term is x2. We know that the energy is strictly decreasing, so this is theta dot. Whenever x2 is not equal to 0, that we can say very clearly. So let's take a note of that. First point is, if we are not at the equilibrium point, which is the origin, if the system is not at the equilibrium point, let's write it as EQ point, then dE by dt is less than 0 if x2 is not equal to 0. Furthermore, if x2 is equal to 0 and it's a non-fixed point, furthermore, if x2 is equal to 0 at a non-fixed point, then we can show that it doesn't remain there, meaning the higher derivatives make x2 change its value to some other, from 0 to some other value. Owing to this, what eventually happens is the pendulum's energy keeps on decreasing. Let's make that important observation now. The energy keeps reducing until it reaches the minimum value. What is the minimum value? That is minus mgl, which occurs when cos theta is equal to 1 and theta is equal to 2k pi. Let's write it here. Theta is equal to 2k pi, meaning eventually our system did settle down to or exactly at the equilibrium point, meaning the equilibrium point is asymptotically stable. Implies the equilibrium point is asymptotically stable. Observe here that in this case, we did not really compute what xt looks like. So all these epsilon delta stability notions, they depend on how exactly the trajectories vary with time. In this case, rather than looking at the trajectories, we looked at the energy of the system. And from the energy approach, we showed that eventually we could show exactly the same results. Meaning, sometimes we can design energy-like systems which can help us study the behavior of the given nonlinear system. So Lyapunov functions generalize the notion of energy functions to more general systems. So Lyapunov functions need not exactly be energy functions, but they are energy-like functions. They are positive definite near the equilibrium point, and then If the equilibrium point is asymptotically stable, then V dot, the energy function, keeps on reducing until it reaches the equilibrium point, which is the origin. So with this, we now understand the importance of why Lyapunov functions need to be used, and let us formally define the same. With this, we define a Lyapunov function. Let the Lyapunov function V, let's write it, V, the Lyapunov function then V is it satisfies a few nice properties. First is, let's highlight all of the properties here. V is a continuous map from Rn to R. Additionally, so the Lyapunov function V is a function of the states in the system. So let's rather write it as V of X, where X is the states of the system. V of X is locally positive, semi-definite, so what is the meaning? Okay, let's complete it. It is locally positive, semi-definite around the origin. Why the origin? Because around the origin, because origin is our equilibrium point. And additionally, what does it mean that it is locally positive semi-definite? It means the following. First is V of 0 is equal to 0 and V of X is greater than 0 for every X such that the norm of X is bounded above by R1, some R1, which is some number greater than 0. All that it says is we do not want this V, the function V, to be positive definite in the entire domain. That is not required all the time. Rather, it is enough for us to say that Vx is locally positive definite. It takes the value of 0 only at the origin, and otherwise in every point in the vicinity of the origin, its value is strictly greater than 0. But not only this, it has to satisfy a few more properties as well. What are those properties? They are Vx is, it has to be differentiable and its derivatives along the trajectory. So I'll soon explain what do we mean when we say derivative along the trajectories. But let's continue with the definition now. So we say that additionally, V of X is differentiable and its derivatives along the trajectories of the system. Is again locally negative semi-definite. Meaning, what do we mean by negative semi-definite? We say that v dot of x is less than or equal to 0 for every x such that the norm of x is less than now some R2. Here R2 is obviously some number, R1 and R2 take values greater than 0. So let's look at the definition which we have written now. So we say that a function v is a candidate for a Lyapunov function if it satisfies all of these properties. The first property is that, first of all, it should be a continuous map from Rn to R, meaning much like an energy function, it must be a real valued function. Secondly, we say that near the origin or near an equilibrium point, it must satisfy a few more properties. The first property is that it must be locally positive definite. The second property is that v of x is locally positive definite around the origin. What do we mean by locally positive definite around the origin? It means that first is v of 0 must be equal to 0, and the second is v of x must be strictly greater than 0 for every x in some R1 neighborhood of the origin, or we can say such that norm of x1 is less than some R1, where R1 is some positive number. So what we are saying here is v need not be positive definite in the entire domain. No, just around the origin, it must be locally positive definite. There's yet another important property, which is the third property, which says that v of x is differentiable. And its derivatives along its trajectories is, let me highlight it, locally negative semi-definite. So there are two things that have come in here. First is locally. That means, again, this behavior expected in some neighborhood near the origin. Second, it has to be negative semi-definite. What do we mean by negative semi-definite? It simply means that v dot of x is less than or equal to 0 for every x in some R2 neighborhood of the origin, where again R2 is greater than 0. So this is our Lyapunov function. The Lyapunov function must satisfy all of these properties. The first property is it should be a real valued function. The second property says that around the origin, it must be positive definite, meaning it should be equal to 0 only at the origin, and every other value in the vicinity of the origin, it is a positive number. Second is, and the third property, is that it must be differentiable and its derivatives along its trajectories must always be negative semi-definite. Any function that satisfies all of these properties is a Lyapunov function for the given system. We mentioned one more term here, which, let me explain what that term means. That is, its derivatives along its trajectories. What do we mean when we say derivative along its trajectories? So let's try to understand that, and after that, we'll state the conditions for stability. So we know that the Lyapunov function that's given to us is let's say, differentiable. then we say that the derivative of v of x along its trajectories is computed in the following manner. V dot of x is equal to, let's say x is the state vector and its dimension is n cross 1 as shown here. Then v dot can be written in the following manner. Dou v by dou x1 times dx1 by dt plus dou v by dou x2 is dx2 by dt. This goes on up to dou v by dou xn times dxn by dt. Now, what are all these values? These values are nothing but the system state space representation is x1 dot, which is dx by dt. So dx1 by dt is equal to sum f1 of x. So again, we are looking at an autonomous system. Dx2 by dt is sum f2 of x, and so on, such that dxn by dt is equal to fn of x. Substituting this here, we get v dot of x is equal to dou v1 by dou x1 times f1 of x up to dou vn by dou xn times fn of x. And we know that f of x is nothing but the vector containing the terms f1 of x to fn of x. Hence, we can further simplify it a bit more and write v dot of x is simply equal to, you can say, dou v, or this is dou v by dou x in general multiplied by fx, where dou v by dou x is equal to this value. Sorry, why? There should not be any v1 or v2. This is simply dou v by dou x1 and dou v by dou xn. Okay. So then dou v by dou x is this row vector, which is equal to 1 up to dou v by dou xn. So when we take the derivative of v dot of x in this manner, then we say that the derivative is along the trajectories. So the trajectories of the system are governed by the state space equation in this manner. Since v dot depends on f of x, which actually dictates the trajectories of the system, we say that this is the derivative of vx along its trajectories. Meaning, so now we can say the following important things. Suppose it's highlighted here. If v dot of x is actually less than 0, this implies that v increases along the trajectory as we move along the trajectory. Similar to this, if v dot of x is now less than 0, this implies that v simply decreases along the trajectory. So meaning, as we move further and further along the trajectory of the system, the Lyapunov function, its value keeps on decreasing. So this is why we say in the definition of the Lyapunov function that its derivatives along its trajectories, write it as its derivative along its trajectory keeps on decreasing. With this, we are now ready to state the stability theorem using a Lyapunov function. And it's defined in this manner. It's known as Lyapunov's direct method. Lyapunov's direct method says that consider an autonomous system x dot equals f of x, where f is, we assume that f is locally Lipschitz. Locally Lipschitz in the domain D. So this is required such that our solutions or the solutions from this nonlinear system are not only do they exist, but they're also unique. Okay. Then we say that suppose we can find a scalar continuously differentiable function, differentiable function say v of x such that v of x satisfies some nice properties. The first property says that suppose we can find a function v of x such that it satisfies all the three properties that we discussed before. What are those three properties? First is it must be scalar valued, meaning from Rn to R. Second is it must be locally positive, definite around the origin. Third property, it must be locally negative, semi-definite. Around the origin. Again, what did we start with? We started by saying we have some autonomous system, x dot equals f of x. And for that system, we have managed to find a function v of x, which is scalar valued, locally positive definite, and also negative semi-definite. In that case, we can make this very important conclusion, which is then x equals 0, which is the origin, is a stable equilibrium point. Generally, people also say that it is a stable equilibrium point in the sense of Lyapunov. In the sense of, hence, we have now stated our first result on the stability of the system using a Lyapunov function. All that we have to do is that we have to find a suitable candidate Lyapunov function. If it exists, if we can make sure that the function satisfies all of these three properties, then our job is done. We know that x equals 0 is a stable equilibrium point in the sense of Lyapunov. This is the first condition on stability, but if we are also interested in figuring out whether or not this equilibrium point x equals 0, the origin, is an asymptotically stable equilibrium point or not. Also, is it an exponentially stable equilibrium point or not? Can we also find out these things using the Lyapunov functions? The answer is yes. Let us now derive the conditions for asymptotic stability. Follows quite straightforwardly, actually. Again, we have the same premise. So I'll not repeat it again. We again have an autonomous system, and so let's write it. X equals 0 is a stable equilibrium point, meaning we have found a candidate Lyapunov function which satisfies all the three properties that we discussed before. Additionally, if V is locally negative definite. What do we mean by locally negative definite? We mean that V dot of 0 is equal to 0 and V dot of x is less than 0 for every x in some neighborhood of R2. Meaning, whenever we are not at the origin, the derivative of V is strictly less than 0. Meaning, what eventually happens is, if we start with any initial value of V of x, and if we are not at the origin, then we know that the derivative is negative. So V's value keeps on reducing until we reach the origin. Traditionally, we say that if V is locally negative definite, then the origin is also asymptotically stable. This is it. This is all the condition that we need for asymptotic stability. V dot has to be strictly less than 0. Using Lasser's invariance principle, we can show that we can relax this condition in some way. We'll discuss that later. For now, we know that these conditions will guarantee asymptotic stability. In a very similar way, we can also talk about local, or we can talk about exponential stability. In our previous discussions, we saw that exponential stability implies asymptotic stability and some other nice properties as well. What are those nice properties? It says that not only does the system approach the origin, the rate at which it approaches the origin is always upper bounded by an exponential, by a decaying exponential, which is a slightly stronger condition than just asymptotic stability. For exponential stability, we say that x equal 0 is asymptotically stable. Along with that, we can also say the dot of x, which is equal to dou v by dou x times f of x, the derivatives along the trajectory. They have to be bounded above by this term, minus alpha times v of x. And where, again, in some neighborhood around the origin. So let's write it. This property has to hold for every x such that norm of x is less than some R2, where R2 is greater than 0. Meaning this is again local behavior. So for asymptotic stability, we only said that if you're not at the origin, as shown here, the derivative is strictly negative. Here, what we say is not only is the derivative strictly negative, it is in fact upper bounded by this value, meaning now it is a stronger condition and it tells us also about the rate at which the Lyapunov function reaches the 0 value. If the Lyapunov satisfies this function, then it implies that x equals 0 is exponentially stable. So all of the stability notions that we have discussed so far are local stability notions. That means the origin is either locally stable or locally asymptotically stable or locally exponentially stable. When can we talk about the global properties? Only when all of these bounds of x that we see here, all of these conditions, they hold for the entire domain. So let's write the conditions for global stability, or write the conditions for global asymptotic stability, which can be similarly extended for exponential stability. So we have three conditions before on the Lyapunov function. First, let's write it this way. The origin is, this is often written as GAS. The origin is globally asymptotically stable if we can find a Lyapunov function v of x such that, again, it satisfies three properties. Now the properties are exactly the same except the term local has been dropped, meaning the first property stays the same. V is scalar valued. Third, V is positive, definite for every x in the domain. And the third property is V is negative definite for every x belonging to the domain. If we can find a Lyapunov function that satisfies all three properties, then we can say that x equals 0 is globally asymptotically stable. Let us now see a quick example of the pendulum system that we saw before. This is a pendulum system state space equation, and on the right hand side, we see a depiction of it. So this is again the same example that we saw before. So can we comment on its stability now in the sense of Lyapunov? Let's try to do that. Let us choose the Lyapunov V as being equal to minus G by L times 1 minus cos of x1 plus half of x2 squared. Let's now try to calculate its derivatives along the trajectories. dv by dt. This is equal to dou v by dou x1 times dx1 by dt, dou v by dou x2 times dx2 by dt. So what is it equal to? Let's write it. Dou v by dou x1 will times this. We get minus g by L sine of x1 times x1 dot. X1 dot is simply equal to x2. And the second term now becomes half x2 squared. So x2 times x2 dot. And x2 dot is equal to g by L sine of x1 that's my bad. In this Lyapunov function, let us choose please delete these parts. Let us choose the Lyapunov candidate as v of x is g by L 1 minus cos of x1 plus half x2 squared. Then the derivatives of the Lyapunov function along the trajectories are given by dv by dt, which is dou v by dou x1 times x1 dot plus dou v by dou x2 times x2 dot. So let us now substitute the values. What is dou v by dou x1? Dou v by dou x1, this is equal to g by L times sine x1 times x1 dot. X1 dot is simply equal to x2. Thus dou v by dou x2 is simply equal to x2 times x2 dot. This entire term. X2 times x2 dot, and x2 dot is now equal to minus g by L sine x1 minus b by ml squared x2. Evaluating this a bit more, we see that. Let's write the whole thing. This is g by L sine x1 times x2 minus g by L sine x1 times x2 minus b by ml squared x2. You see that these two terms get cancelled. So what we are left with is dv by dt is equal to minus of b by ml squared x2, which is less than or equal to 0. So what have we found? We have found a valid Lyapunov function with this. Hence, we can directly conclude that we can directly conclude the following. The origin x equals 0 is a stable equilibrium point. Without solving for the trajectories of the system, we have been able to arrive at this conclusion. However, notice that we have missed out on something important here. We know that not only x equals 0 is a stable equilibrium point for the system, we actually showed that, we saw before that it is also asymptotically stable. But the Lyapunov function is not conveying the same thing. Hence, we will end today's lecture with the important conclusion that if we are unable to find a Lyapunov function, that means that we are unable to make any conclusions on the stability properties of the system. However, if we can find a Lyapunov function, then we can say whether the system is stable or not. So if we can find a Lyapunov function, then we can conclude that the origin is a stable equilibrium point. However, if we are unable to find a Lyapunov function, it doesn't imply the origin is unstable. This is very different from the epsilon delta notions of stability. Using the epsilon delta notion of stability, we knew that if the equilibrium point is not epsilon delta stable, then it is simply unstable. However, in the sense of Lyapunov, if we cannot find a Lyapunov function, it simply means that we have not been able to show, or we have not been able to find a suitable Lyapunov function. Perhaps somebody else might be able to find one. Hence, we cannot say anything about the stability properties of the system or the equilibrium point. Yet another conclusion is that for this example of the damped pendulum system, using the candidate Lyapunov function that we have chosen here, which is equal to this, we could show that the system is, or the origin is a stable equilibrium point. However, just because we could prove that it is a stable equilibrium point does not imply that it is not asymptotically stable. In fact, in this particular case, the origin is in fact an asymptotically stable equilibrium point. So how can we say that? Or can we draw the same conclusion using this Lyapunov function? This leads us to something that's known as the Lassalle's invariance principle, and we'll talk about it in the next lecture. Thank you.